So we're in section 3.5, and we're just going to talk about some applications. So we're going to talk about three different kinds of models today. Exponential growth, and the type of exponential growth that we're going to talk about is y equals a e to the b x. And for exponential growth, we have b is greater than 0. So our exponent ends up being positive. And our exponential growth is always going to look, for this particular kind of model, it's always going to look something like this. And it's going to, our intercept here, the y-intercept, is going to be at 0, a. So a, when we substitute 0 in for x, e to the 0 is just 1. So at x equals 0, y equals a. So this is going to be our exponential growth model. On Monday we're going to do a project that has to do with a slightly different kind of growth model. But anything else is going to be kind of a shift from this growth model. We can shift up or down, and we can shift left or right, but it's going to be essentially the same. And then we're going to talk about exponential decay. So exponential decay is going to be y equals a equals b to the x, and b is going to be less than 0 here. So our exponent is going to be negative. And exponential decay in with this particular model is always going to look like this. And same intercept, 0, a. And I guess I can make it a little steeper there. A little better. So these two particular models are what we're going to talk about. We've talked about one type of exponential growth. That was the compound interest formula. That's a type of exponential growth. Other things that are exponential growth, population can be modeled with exponential growth. When we talk about depreciation, so kind of the opposite of compound interest, when things are losing value, that can be modeled by an exponential decay function. And we'll talk about radioactive decay, when things are decaying due to radioactivity. We can model that with an exponential decay function as well. And we'll also talk about one other, and we'll draw the picture and talk about what it is right at the end. We'll talk about a logistic growth. So what I want to do is just go through a few examples using the exponential growth and exponential decay models. So first example, we're going to talk about population. So our population, and we're in a city, and our population is in millions. And it's modeled by this function y equals 1.8 e to the 0.026x. And where x equals 0 is the year 1980. So before we go on, what is the population in 1980? Oh, sorry, x equals 0 is 1980. So what's the population in 1980? 1.8 million. So I plug in x equals 0, I get 1.8. So the population in 1980 is 1.8 million. So that's where we're starting our model. In what year will the population be above or above 2.5 million? So that's our question. With this model, when will the population be above 2.5 million? So how are we going to set this up? Where does the 2.5 million go? To 2.5 million would be the y. So I'm going to put 2.5 million here. 2500, is that right? 000. Oh, it's the populations in terms of million. Okay, so what do I put there? Just 2.5, okay. That's a mistake that a lot of people make in these types of problems, is the population is million, population is in thousands. So you have to make sure that the number you put in corresponds to the units they give you. 2.5 equals 1.8 e to the 0.026x. And we know how to solve this, right? What are we going to do? Divide by 1.8. So we get e to the 0.026x equals 2.5 over 1.8. And then what do we do to solve this? Take the natural log of both sides. When I take the natural log of this side, all I'm left with is 0.26x equals the natural log of 2.5 over 1.8. And x, I'm just going to write out our numbers here, 1 over 0.026 times the natural log of 2.5 over 1.8. And if I plug that in my calculator, I end up with about 12.6. So in what year will the population be above 2.5 million? If x equals 0 is 1980, what year is x equals 12.6? 1992 in 0.6 is almost 2/3 of the way through. So August maybe? In 1992, sometime a little more than halfway through 1992, our population would be above 2.5 million. Questions there? When we're plugging these things into our calculator, try to keep when you do these, if you do these as intermediate steps, keep 4 decimal places or so you don't lose accuracy, because you can end up with your answer being quite a bit different at the end if you round off too much in an intermediate step. All right, so this next problem is probably the most difficult type of problem that we'll do in exponential functions. So we have a bacteria population. And after 2 hours, the population is 256 bacteria. After 5 hours, we have 541 bacteria. We want to know what will the population be after 24 hours. So we have a fair amount of work to do in this problem. Population growth can be modeled with an exponential function. So this is exponential growth. So we know our function is going to be y equals a e to the b x. Y is our population. And x equals time. Any ideas how we're going to go about this problem? Yes. So we have two data points. We have two x's and y's. So we have the point 256, and we have the point 541. So this is kind of like, and these are each an x and a y. This is kind of like the problem we did on the last test with the parabola, where we're fitting our points to our parabola, and we ended up with a system of equations. Well, this we do end up with a system of equations, but this time our equations are exponential equations. So the first thing we're going to do is we're going to plug in the first set of numbers and solve for a. So let's plug those numbers in. We have 256 equals a e to the 2b. So this is only going to get rid of one of our variables. So to solve for a here, what am I going to do? To get a by itself, divide by e to the 2b. So a equals 256 divided by e to the 2b. What's another way I could write 256 divided by e to the 2b? E to the negative 2b. So I can write this as 256 e to the negative 2b. Now I'm going to put this back into the equation. So I'm going to put this back into the equation and use a second set of numbers. And we're going to use a second set of numbers to find b. So I'm going to put this back into my equation. I get y equals a is 256 e to the minus 2b times e to the b x. And I'm going to plug in my second set of numbers. So I get 541 equals 256 e to the minus 2b times e to the 5b when I plug in the second set of numbers. So I'm going to write that as 541 equals 256. How can I write e to the minus 2b times e to the 5b? What do I do when I multiply these two numbers with exponents? What do we do with the exponents? When we multiply the numbers, we add the exponents. So this is e to the 3b. And now I can solve for b. This is this is exactly like the problem we just did. So we divide by 256. I'm going to turn this around. E to the 3b equals 541 over 256. Take the natural log of both sides. 3b equals the natural log of 541 over 256. And this gives me that b equals 1/3. Divide by 3 to get b by itself. The natural log of 541 over 256. Plug this into my calculator, and I get b is approximately 0.2494. Now I'm going to use this b to solve for a. So I'm going to plug this b in here, and I get a equals 256 e to the minus 2 times b, 0.2494. And I calculate that out, and I get a equals 155.4583. And now I have an a, I have a b. I can plug that into my function. I'll have my model of exponential growth. So I'm going to go to the next page here. We end up with y equals 155.4583 e to the 0.2494 x. So there's my exponential growth function. There's the growth function. And the problem asks us what is the population after 24 hours. So I'm going to plug in 24 for x. So I get y equals 155.4583 e to the 0.2494 times 24. Put that in my calculator, and I get y equals 6189.710 is what I get when I plug that in. Can we have 0.7 bacteria? No? They're going to multiply one at a time. So we would say our population is 6189. 61819. That's what I get there. So we'd say our population is 61,819. So we will round down because there's no such thing as 0.7 bacteria. So with this type of problem where we need to find our exponential growth function, and we have 2 points on our curve, we plug in 1 point to solve for a. We use that value of a and the second point to solve for b, and then we get that will give us our growth function. So it's like solving the system of equations. It's just a little bit different because we have this exponential function. Use 1 point to find one of the constants, use the other point to find the other constant. All right, questions there? So that's probably the most complicated type of problem that we end up doing. All right, radioactive decay. Radioactive decay is an exponential decay model. So we have y equals a e to the bt. For radioactive decay, a is the initial amount. And b for radioactive decay is always, and we talked about this a little bit yesterday, the natural log of 0.5 divided by the half-life. And we find the half-life just like we found the doubling time. We would solve for 1/2 equals e to the bt, and we want the time when we get half the amount that we have. And it turns out that b is the natural log of 1/2 over the half-life. So this is always going to be the case for radioactive decay. So let's do a quick example using radioactive decay. So let's say we have radium 226. Has a half-life of 1,620 years. How much will we have if we start with 5 grams? How much will we have after 10,000 years? And we've done a problem like this before where we had the numbers and we plugged the numbers into this function. We just didn't know what exactly the problem was about. But we solved this. We had the numbers for this. So we're going to say this is our radioactive decay model. We know that b is natural log of 0.5 divided by the half-life. So we can say y equals our initial amount is 5. E to the natural log of 0.5 over our half-life of 1620 and times 10,000. So this whole thing is our exponent. So we're going to plug this into my calculator, plug it in, calculate, and I get y equals about 0.07 grams. And I'm just going to put that in my calculator and calculate. So after 10,000 years, if we have 5 grams, we're still going to have about 7/100ths of a gram of radium-226. Still radioactive. All right, questions there? All right, last type of exponential growth, logistic growth. Logistic growth is an exponential growth model, and logistic growth is always going to have a function that looks like y equals a over 1 plus b e to the minus r x. A is normally called the carrying capacity. And b and r are positive constants that are determined by the situation. And to find b and r, that's something that you need calculus to be able to figure out b and r, and it's something that you'll do in calculus. Is you do a logistics growth and you starting with the equation and figure out b and r. It's a little too much for us to do, but a is our carrying capacity. Logistic growth happens when we have something, population growth, when we have some kind of limiting factor. So there's only a certain amount of food. There's predators that are eating the animals, so the population can only can't grow beyond a certain point. If you're talking about a disease growth, there's only so many people that can get sick at a time, so that limits the growth of the disease. So that would be logistic growth. Logistic growth looks like our curve in general is always going to look something like this. So logistic growth increases, and then eventually it levels off. And this, where the logistics growth levels off, we get a horizontal asymptote at the carrying capacity. So, for example, the example that I gave about like diseases spreading, the carrying capacity would be the number of people that could possibly catch the disease. So the population can't spread beyond however many people can catch the disease. And we also have a horizontal asymptote down here at y equals 0. So the population can't get below 0. And what happens is there's this point kind of in the middle where in this area the growth is increasing. And then here the growth slows down. So the growth is decreasing. So initially, with logistics growth, the population is growing faster and faster. It hits some point and then it slows down, and eventually it's going to level out. So logistics growth is always going to look like this. And that's where we have growth, but with some limiting factors. And we did, not last night, but the night before, we had a problem where we were solving for some piece of this logistics growth equation. So let's take a look at a quick example of that. We have a game preserve. And we have released 100 animals. And the managing agency believes that the carrying capacity is 1,200 animals. And they've estimated, they've done their calculations, and they say the population can be modeled by this logistic growth function, y equals 1,200, our carrying capacity, divided by 1 plus 8e to the 0.1588, negative 0.1588t. So we didn't have to figure this out. They figured it out for us, and they told us this is the function that's going to model the population. Our question is how long to reach half the carrying capacity? So, how are we going to set this one up? What is half of our carrying capacity? 600. And where is the 600 going to go? Y. That's our Y. So we want to find, our equation is 600 equals 1200 over 1 plus 8 e to the negative 0.1588 t. And we want to find t. So how do we go about finding t here? Multiply, we want to get rid of this in the denominator. So I'm going to combine two steps here. I'm going to multiply both sides of the equation by this denominator, 1 plus 8e to the negative 0.1588t, and I'm going to divide both sides by 600. So multiply both sides by this, divide both sides by 600, and I get 1 plus 8e to the negative 0.1588t equals 1/2. Or no, 1/2 equals 2. 1200 divided by 600 is 2. I want to get the exponential function by itself, so I subtract the 1 and divide by 8. So I get e to the negative 0.1588t equals 1/8. So I'm subtracting the 1, dividing by the 8. And now I can take the natural log of both sides. I get negative 0.1588t equals a natural log of 1/8. Divide by negative 0.1588. So t equals 1 over negative 0.1588 times the natural log of 1/8. Plug that into my calculator, and I get that this is approximately 13 months. Thank you. So it would take about 13 months to reach half of our carrying capacity. Questions there? All right. So on Monday we'll have we're going to do an activity that has to do with a slightly different kind of exponential growth model. Not a lot different. And then we'll review on Tuesday, have Pi Day on Tuesday, and our test is next week on Friday. There you go.